Okay, now in this final topic that we are going to introduce you, right, on probabilistic method, we will see a couple of applications of the probabilistic method, just to see a very short introduction to this technique. So now let us just take a quick review of some definitions from probability theory, which you must already be familiar with. So we have omega, a finite set, which we call the sample space, and then let's say p maps from omega to 0 and 1 as a function, which we call the probability function. If summation x belonging to omega, p of x is equal to 1, right? Then we say omega p is a probability space. Now, as an example of omega, we have the 6 sides of a fair dice. Let's say the unbiased dice, if I toss, it will have the same probability of any of the numbers like 1 to 6 turning up. So the probability of any particular phase is 1 over 6, right? So therefore 1 over 6 is the probability for each of the 6. The sum overall I, p of I, where p of I is the probability that the side with the number I comes up, is equal to 6 into 1 over 6, which is 1. So the sum is equal to 1, therefore we have a probability space. Now the the tossing of the dice, or like other things like this, which defines the probability, is called a random experiment. So random experiment is basically choosing some element of omega at random with the probability p of x, right? So once you have the distribution p, right, in the probability space, right? Once that is fixed, then we need to be able to choose the elements with that probability, right? What is the probability for x? That is precisely p of x. Now, if we are allowed to choose, or we are able to choose this way, then we say it's a random experiment under this probability space. Now, any subset of the event space omega is called an event. Of the sample space omega is called an event. So choosing a subset of this event, subset of this element is an event. So the occurrence of, for example, the even numbered phase of the dice is an event, because when I toss a dice, any of the 6 numbers can come out. I will say that, okay, if it is an even number, then I will win. So therefore, the event that I win is related to the outcome becoming an even number. So that is the definition of an event. Similarly, an example is outcome is a prime number, right? So it's either 1 or 2 or 3, or 2 or 3 or 5. Then it's a prime number. Then it has the same probability. For example, we will see as the chance of getting an even number in the case of fair dice. Now, probability of an event is defined to be the sum over all the probabilities of the individual elements of omega, right? So summation over all x belonging to E, p of x, gives the probability that some element of E is selected. Okay? That is the probability of the event E itself. Now, if for every x in omega, the probability of x is equal, right? It's equal to 1 by the cardinality of omega, because the sum must be equal to 1, right? Then P is said to be a uniform distribution, right? So the probability distribution is uniform if all the elements has the same probability of occurring. Then if I have two events A and B, right, and the complement of the event is omega minus A, and the union of two events has the probability equal to probability of the sum minus probability of the intersection. And similarly, we have an important result which we'll be using. It's called the union bound. If you take the union of some events, A1 to AN are events, then the probability of union AI is at most the summation of the probabilities. I mean, this is intuitively clear, but this is a powerful tool as well. So we will see the use of it. Okay, so with this, let us look at some application. So we are going to look at one of the earliest applications known in this, that is to obtain a lower bound for the Ramsey numbers that we talked about. So let us say that we have a graph which is a complete graph on n vertices, and the edges of this graph are colored with two colors, red or blue. Now a subset of vertices is called monochromatic, right? If you remember, if all the edges of the subgraph, right, induced by the vertices of S, all have the same color. Now the Ramsey number R of t, as we defined earlier, is the least positive integer n, such that every red-blue coloring of the complete graph Kn contains a monochromatic KT. So as we said, Ramsey theory is about finding orders in disorder when the numbers becomes large. So when the n is large enough, we are saying that any red-blue coloring, whatever, no matter how you are going to color, you can find a monochromatic KT, that all the T choose 2 edges of the KT are going to be of the same color. So here is the proof by Erdős, right? So he claimed that, I mean, the theorem states that if the n choose T, right, n and T are such that we are looking at KT, right, complete graph on T vertices where all the edges have the same color. N choose T times 2 raised to 1 minus T choose 2, right, is the less than 1, right? So if n and T are such that n choose T into 2 raised to 1 minus T choose 2 is strictly less than 1, then the Ramsey number R of T is larger than n, right? So it says that the Ramsey number must be large enough, right? And as a consequence, one can actually show that Ramsey number is larger than 2 raised to floor of T by 2, right? Which is like exponential in T by 2, right? That's a quite large number for every T greater than 2. Now the proof is by using probabilistic method, where we use the following random experiment. Okay? So for every, so you take the complete graph on n vertices. Okay? We start with the complete graph on n vertices. Let us say Kn. For each edge of the complete graph on n vertices of Kn, toss a fair coin, right, to decide what is going to be the color of the edge. So every edge I am going to color by picking up a coin, tossing it. If it becomes heads, then I will color it, let's say, red, and if it becomes tails, I will color it with blue. And we'll assume the coin is fair, so that the probability of red or blue is the same, right? So if I take a random, a graph on n vertices and give such a coloring, and then any possible coloring that we want will come out as an outcome, right? I mean, one of them will come, I mean, any of them can come out as an outcome. So therefore, all possible colorings are there. Right? Now, let us say that if you look at, the Ramsey number R of T, if R of T is larger than then of course we know that the Kn has a red-blue coloring, which does not have a monochromatic KT, right? So if the Ramsey number is larger than n, then the Kn has a coloring where there is no monochromatic KT. Because if n was larger than R of T, then any coloring, no matter how, right? That's the definition of the Ramsey number. No matter how you are going to color, you will end up in a monochromatic KT, right? So therefore, if I can show, right, if I can show that there is a coloring, right, if n is with this property, then there is a coloring where there is no monochromatic KT, or then we are done, right? So the idea is something like this, right? Suppose you have real numbers x1 to xn, and I tell you without telling what are xi's, I am going to tell you the average of these numbers, right? I don't tell you what is n, what are the numbers, nothing, right? I tell you that the average of the numbers, summation xi by n, for whatever xi and n are, is greater than or equal to a. You can immediately conclude that there should be at least one of the xi's which is greater than or equal to a, right? Because average is greater than or equal to a, one of the xi's must be greater than or equal to a, because otherwise, if every number is less than or equal to is less than a, then the average will also be less than a. So that is, so without knowing what are the numbers, without knowing how many are there, we can still say that at least one of them must be larger than this. So the same idea we can use in probability, right? If I can show that probability of something existing is positive, then it must exist. So let us say that AS is the event that the induced subgraph on the set of vertices S is monochromatic. That is, all the vertices get the same color. Now, if the number of vertices in S is actually equal to T, then what is the probability of the event AS that all the edges get the same color? Well, for every edge, the probability that it gets a fixed color red is 1 by 2. So since there are t choose 2 edges in the graph, 2 raised to, 1 by 2 raised to t choose 2 is the probability that all the product of the probability, because each coloring is independent of the others, so we can multiply it to get the probability. It is 1 by 2 raised to t choose 2 is the probability that it is all colored red, all the edges are red. But to say monochromatic, I can be happy with either all red or all blue, right? So now that is 2 times this number, right? So therefore 2 times 2 raised to minus t choose 2 will give you the probability of AS. Now, for a fixed subset S, the probability is this one. Now, let us look at the probability of the union of AS for every subset of the n vertices, right? A subset of n, where the cardinality is actually equal to T. So, all the T element subsets, how many are there? N choose T element subsets of n element set are there. Now, by union bound of the probability that we just learned, probability of union AS is less than or equal to sum of the probabilities of AS over all the subsets that we are looking at. So, it is summation over all T element subsets of n probability of AS. Now, how many T element subsets are there? N choose T are there, and probability of AS is 2 raised to 1 minus T choose 2 as we just proved earlier. So therefore, this is the upper bound of probability of the union AS. What is the union AS? The event union AS is that, right? AS is that a fixed subset is monochromatic. Union AS is that at least one of them is monochromatic, right? If the probability that one of them is monochromatic is this, then we are finding an upper bound for that by the identity, right? So we have probability of union AS that at least one of them is one of the T elements of that is monochromatic is we have shown is less than or equal to n choose T into 2 raised to 1 minus T choose 2. But by our assumption of the problem, this number is strictly less than 1, which means that the probability that one of them is monochromatic is strictly less than 1, which means that probability of none of them is monochromatic is strictly greater than 0, right? Complement. The complement event is probability that none of them is monochromatic, that is strictly greater than 0. Probability of intersection AS bar, right, the complement of AS is 1 minus probability of this, which is strictly greater than 0, because this part, right, this is strictly less than 1. So therefore the complement has positive probability, which means that the probability that there is some coloring, right, red blue coloring, where there is no monochromatic KT is positive. So which means that n choose R of T must be greater than n, right? Now, then from this, right, one can use some some combinatorial identities and the inequalities to actually show that some approximations will help you show that these numbers correspond to t being n being less than not less than greater than now r of t being greater than 2 raised to ceiling of t over 2. Okay. So for that you can use this following inequality that k factorial is greater than 2 into k by e whole raised to k. So using this and the identity that we showed here, right? Then choose t into t raised to 1 minus t choose 2 is less than 1. Okay, so that is one example using using the probabilistic method. Let us look at one more. This time we are going to use linearity of expectation. So just to complete the argument, we will just mention what is a random variable. So random variable is basically a function, right? From from omega to real numbers. So a function x mapping from omega to r is called a random variable. Now, examples of random variables are the following, like for example, x is some integer chosen uniformly from the set 1 to n, right, where omega is the set 1 to n. Then x is a random variable. Then I can define y to be the number of prime divisors of x. Then y is a random variable. Then I can define z to be 2 times x. Then z is also a random variable, right? When basically any such real valued functions. Now, probability of x is equal to s is the probability of the event that x inverse of s, right? The x is a function, therefore x inverse of s is a set of all x in omega, where x of small x, which is the element of omega, is equal to s, right? So all the elements mapped to s under the random variable x. Now the events are themselves random variables taking values 0 and 1. To just see this, let us define the indicator random variable for an event as given an event A, xi of x is equal to 1 if and only if x is in A. Right? So for every so whenever this event happens, right, then what happens? We get the the value to be 1, and otherwise it will be 0. So therefore, this is basically right. X of a is basically identical with the event A, because once you know what is A, but we know what is xa, and what is xa, we know that the indicator and the variable basically tells whether A has happened. Now the expectation of a random variable is defined as summation over all the all the values taken by the random variable x, let's say s1 to sm are the values. Then summation I equal to 1 to m, the value times the probability that value is taken by the random variable. So si times probability of x is equal to si. And this is equal to, we can see it also as a summation over all the elements in omega, x of x into probability of x. So now what do we have? So here is an example, right? So for random variable, x is the number of spots on the top of a random toss of a pair dice. Okay, so I'm tossing a pair dice, and what is the top number of spots? What is the expected number of spots we can talk about, right? So what is the expected number of spots, right? E of x is basically sum over all the values x equal to 1 to 6, because then the variable can take any value from 1 to 6, the number of spots on the top, right? But the probability for each one is 1 by 6, because of a die we are rolling. So which is summation x into 1 by 6, x is ranging from 1 to 6, which is 3.5. Okay, now let us look at another result on this. It's called the linearity of expectation. So the expectation of several random variables, suppose you have several random variables, and you have some real numbers, let's say x1 to n, alpha 1 to alpha n. Then the expectation of the random variable that I can make by taking the summation of the random variables scaled by, let's say, alphas. Okay, so alphas are real numbers. Alpha I xi is a random variable because if xi is a random variable, alpha I xi is also a random variable, right? So summation alpha I xi is also a random variable. Now the expectation of this is the summation of the expectation. So summation alpha I into expectation of xi. This is a nice property and very useful. We are going to use this to prove some nice theorem. So what is the theorem that we want to prove? Okay, so we have we have graphs, we have directed graphs. Now we have an oriented graph is basically a directed graph obtained from a simple graph by giving arbitrary directions to its edges. Okay. So take an orientation of a simple graph by taking every edge and decide which way it should be oriented. So an example here, take on the graph G, I have given several possible orientations. Right, each one on the right side is an orientation of the graph, right? So this is called an oriented graph. So we start with a simple graph, we get a simple oriented diagram. Now, if I start with a complete graph for the orientation, then what I get is an oriented complete graph, which I call a tournament. It's called a tournament because, if there is a tournament happening between, let's say, n players, and then each of them are playing, then the outcomes of the play, right, like, who beats the other person can be represented by this kind of arrow, right? And it has many applications, and therefore it's called a tournament. So I take a complete graph, several orientations, each one gives me a tournament. So there could be several tournaments on a given graph. Now, if you recall, graph theory, a path in the graph is basically a sequence of vertices and edges where, right, the consecutive vertices are connected by the edge that comes in between. A Hamiltonian path is a path where all the vertices are appearing in the path. If that is possible, then it's a Hamiltonian path, and the graph is Hamiltonian if I can find a cycle who is also including all the vertices. Now, a directed Hamiltonian path in a directed graph is basically the same, but where all the vertices are present, but the edges must be in the correct order, right? So V1, V2, V3 to Vk is a path. Then V1 to V2 must be, the edge going from V1 to V2, V2 to V3, etc. Now take any tournament, right? So take any complete graph, you take an orientation, any orientation that you want. Then one can easily show that this tournament has a directed Hamiltonian path. Every tournament contains at least one directed Hamiltonian. Now this is a nice result and very easy to prove. I want you to think about this for some time and prove it yourself before you go further. We are not going to prove this theorem. This theorem is very easy. We will just give a sketch of the proof. But we are going to prove something more using the probabilistic method. So here is what here is how you prove the previous theorem. So we take a maximum length directed path in the tournament T. Now since it is maximum length, it cannot be extended. So if U1 and UK are the endpoints of the path, so U1 to UK is a path. Now if I have all the vertices, it is a Hamiltonian path. Right? If it is not there in the tournament, there is some vertex which is outside. So let's say X is the vertex outside. Now, if X is outside, of course, X is connected to all the vertices, right? In the complete graph, all the vertices are connected. But now, the edge direction cannot be from U1 to X because cannot be from X to U1 because U1 to UK is a path. X to U1 is an edge, X is outside the path, then X U1, then U1, U2, etc. UK is a longer path. But we started with the maximum length path. So therefore, the orientation from U1 is to X, right? Now, similarly, UK cannot be going towards X because if UK to X there is an edge, then U1 to UK, and then UKX is another longer path. So therefore, the edge must be from X to UK. Now with this, can you show that there must be a longer path? Okay. We said that UK to X cannot be an edge, and similarly X to U1 cannot be an edge. Now can you use this information to show that there must be a larger path, and therefore there is a Hamiltonian path? Okay, if you thought about it, here is the proof that U1 to UK, I have these vertices in the path, and the edges from X to U1 to UK are there. Okay. Now since U1 to X is an edge in the direction U1 to X, and X to UK is in the direction to UK, when I go from U1 to UK in the path, at some point the direction must change from going from UI to X to the next one, X to UI plus 1, because the direction must change at least once, because the direction at the end point is different. So when it changes the direction, I have U1 to UI, there is a path. Then UI to X, there is an edge. Then X to UI plus 1, there is an edge. And then UI plus 1 to UK, there is an edge. So therefore, I can make another path, right? U1 to UI, UI to X, X to UI plus 1, and UI plus 1 to UK, which is a path of longer length. But this is a contradiction, because we assume that there is no larger path. So since I can extend this any number of times, I will get a path including all the vertices. So it will stop only if there is no vertex which is outside. And so it proves that there is a Hamiltonian path in any tournament. But we want to prove something stronger. We want to prove that there is some tournament where the number of Hamiltonian paths is very, very large. So we will show that there is a tournament where the number of Hamiltonian paths is n factorial by 2 raised to n minus 1. Now n factorial grows much larger than 2 raised to n minus 1. So therefore, this is a huge number. Now how do you prove this? Okay. So to prove this, let us see how we design a random experiment, right? So we want to use probabilistic method, we have to design a random. So what we know is that we are talking about tournaments, right? Tournament is basically an orientation of a undirected complete graph. So therefore, let us start with a complete graph. And now, to bring in probability, what I can do is to give different directions to the edges to make it a tournament by tossing a coin, right? So every edge I orient by tossing a coin. Therefore, I get a oriented graph, which is a tournament. So therefore, this is one way you can bring in the probability, right, into picture. Similarly, depending on what is the probability of the toss, right, the decision to color, not color, the orient, you will get uniform or non-uniform distribution. But we can bring in probability. Similarly, when we are coloring things, we can, as in the previous example, we can bring in probability again by tossing a coin to decide the color, right? So that way we do it here also. So we start with the complete graph, and uniformly and independently at random give each edge a color, each edge an orientation, U to V or V to U. Now the resulting direct graph is of course a tournament, because all the edges have been oriented. Now suppose V1 to Vn are the vertices of the tournament on n vertices Tn. Then any permutation of of the n vertices defines a path in the undirected graph, right? The K. Right? But this path may not be a directed path. So therefore, I just look at the permutation sigma of the n vertices. So there are n factorial such permutations. Each permutation will give me a path in the undirected graph. Now I want to check whether it gives a path in the directed graph, right? So in the tournament. So to do this, I define a random variable, indicator random variable, S sigma, which says that if sigma is the permutation which corresponds to a directed path or not. So if sigma is a directed path, then I will say x sigma is 1, and otherwise it is 0. So sigma of 1, sigma of 2, etc., sigma of n decides the order, right? V sigma of 1, V sigma of 2, V sigma of n decides the order of the vertices that we are taking. Now, if V sigma of 1 to V sigma of 2 is an edge in the direction R, similarly, V sigma 2 to V sigma 3 is an arc, etc. All the way, then we say that this is a directed path, and therefore in the random tournament we have this is a directed path, and therefore a sigma is 1. So the indicator random variable says that sigma is a good permutation, right? So it's the indicator random variable that sigma corresponds to a directed path. Now, what is the probability of the random variable taking the value 1, right? The probability that the sigma gives a direct path. Well, each edge has the probability that it is in the orientation u to v or v to u to be the same, right? Now, if v sigma 1 and v sigma 2 are taken, then what is the probability that the edge is from v sigma 1 to v sigma 2? Because we decided to give the direction in either way with the same probability, it is half for one of them, right? So with probability 1 by 2, I have this. But then this is true for every edge, and in the Hamiltonian path, right? We're not in the Hamiltonian path, not in the n vertex path, there are n minus 1 edges, right? v1 to v2, v2 to v3, etc. vn minus 1 to vn. So the n minus 1 edges all must be in the correct order, and the probability for this, right, happening is probability that this happen is 2 raised to 1 minus n, right? 1 by 2 whole raised to n minus 1. So the probability that x sigma takes the value 1, the indicator random variable x sigma takes the value 1, or the probability that sigma is a directed path is 2 raised to 1 minus n. Now the expectation of sigma, right? Expectation of x sigma is the probability that it takes the value 1, because for a random indicator random variable, the probability and expectation are the same, right? Because the definition of expectation says that you take the value and multiply with the probability and sum over all the values. But now the probability that it takes 1 is the expectation, because we are multiplying with 1, right? Probability with 1. Whenever it takes value 1, we will multiply with that, otherwise it is 0. So the expectation of random variable is the probability that it is equal to 1, which is 2 raised to 1 minus n again, right? Now 2 raised to 1 minus n previous was the probability, now it is an expectation. Now the linearity of expectation says that if I sum over all these events, let's say for all the sigma in Sn, right, all the permutations, then expectation of the sum is the sum of the expectation. So what is the the sum as a random variable? The sum as a random variable takes x sigma and check whether it is 1 and then adds to the sum, right? So what am I adding? I'm saying that whenever sigma is a good path, it's a directed path, I'm counting 1, which means that x sigma, the summation x sigma is a counting variable which counts the directed paths in the directed Hamiltonian path in the tournament, right? In the random tournament. So since this counts the number of directed paths, we are counting the expected number of directed Hamiltonian paths, right? So expectation of the Hamiltonian path is summation over all the permutations, expectation of x sigma by linearity. But this, there are n factorial of them, and the probability, expectation of x sigma is 1 by 2 raised to n minus 1. So therefore, the expectation of the sum is n factorial by 2 raised to n minus 1. Now, if the expectation of a random variable is something, then there must be at least some occurrence of the random variable which takes that way, right? Because if for all, just like in the case of averages, if for every time, right, the random variable takes a value less than k, then the expectation also will be less than, right? The expected value which is coming will be less than k. And that is the proof, right? So it tells that since the expected number of random variables, Hamiltonian paths is n factorial by 2 raised to n minus 1, we also have that there should be some tournament where the number of Hamiltonian paths is this many. So that is what we've done. And using this observation that a real value random variable has expectation k, then for some instance the variable must take a value at least k. So therefore the tournament has this many Hamiltonian paths, at least some tournament. So we show that there is some tournament with this many Hamiltonian paths, but the method does not tell you how to find this way, right? Does not tell you how to find a tournament. It shows that there is some tournament without ever telling you how to find this. So that is it. So we have the introduction to this method. Now there are many other techniques, as I mentioned, we can look at, but with these two final homework questions, I will wind up. So if v1 to vn are vectors of unit length, right, and lambda 1 to lambda n are plus or minus 1, right, numbers plus or minus 1, then can you show that the modulus of lambda 1 v1 plus or the length of the vector lambda 1 v1 plus lambda 2 v2 plus extra lambda n vn is less than or equal to n for some choices of lambdas, and for some choices of lambdas we can show that the length of lambda 1 v1 plus extra lambda n vn is greater than or equal to root n. So this is a nice exercise for you. Okay, so that's it. So with that, we stop this introduction for the linear, probabilistic method, and with this we also wind up the course combinatorial. So we have learned several tools, and we have introduced 3 topics like species, and then the linear algebra method and probabilistic method, which are all advanced introduction topics in which one can work on. And then there are, of course, other topics that we mentioned. So that's it. So see you later sometime.